Okay, this thing is working. So thank you for the warm welcome. This is my first time in Boston, and the city is amazing. I kind of imagined something else, but it's quite charming, and the people are really lovely and we're really caring, as we can see from the organizers of this conference. So just to give you a little bit of context about myself, I come from Europe, Croatia, which is this tiny little country, you know, right there where the blue arrow points. We are sea neighbors with Italy, so Georgia and I should get along really fine. When you think of Croatia, when you hear of Croatia, it's basically beautiful coasts and seaside, and you get a nice vacation there during the summer. Also, if you're a fan of Game of Thrones, this is where they film it, actually in this city, which basically makes this place useless during the summer. You cannot move. Actually, there are police controlling the lines on the squares because there's no place to kind of move and walk around and explore the city. I work at a company called Asseco. We are basically doing security, ATMs, all kinds of special storages, mobile banking, and it's a big company. We have a subsidiary in a few countries. One is in Croatia. And my purpose there is to act as a business analyst and a project manager, which means that with all my experience with Android, I get to tell people what to do, but also a little bit on how to do it, because we all know that developers love when managers tell them how to do something. So our topic today is, first of all, I need to keep you occupied and engaged for the next 40 minutes, and after that, release you to lunch. So let's get to it. So we will start this presentation by defining what is a certificate. Certificates are everywhere around us, and they are a basic security mechanism that's basically wherever you look. You have it on web, you use it on Android basically every day, and not a lot of people take notice of it until something goes wrong. I'm here to share some of the items and the events that have gone wrong. Hopefully you will learn from my and my colleagues' experience and not do the same later on. So, what is a certificate? It's basically a document that says that any kind of key, a public key that's in it, belongs to somebody. So it proves ownership. So in European Union and some other countries, certificates are used in addition to, let's say, signatures, to sign documents. It's actually a legal form of proving something. You can actually open up an account, or you can get your legal data from the bank or the government just by using some kind of certificate that's provided to you by one or two or three authorities in the country. So what does it look like? There's something called the X509 structure. It's kind of a definition of what needs to go in a certificate. So basically, we're talking about some kind of serial number, ID, the issuer name, let's say how long it's valid, from when till when, and stuff like that. And what's the most important part, you're exposed to certificates every day. So every time you shop online, every time you log on to Google or some kind of service, hopefully to all of your services, there are certificates in play. Now, each time some kind of web browser communicates with the server needs to say, okay, here's my certificate. This is how I can prove to you that I am who I am. And that's basically the basis of this whole security thing. You have the identity in a certificate, basically who is saying that they're Google or that they're Facebook or that they're any kind of entity in the world that wants you to communicate with them. Usually supply names, address, city, any kind of other information that you need to do to be able to verify who you are. And after you do the identity part, you kind of need to define a public key. But when I say a public key, it's obviously accessible to everyone. But why don't I say a private key? Generally, which we will see later on in the presentation, the cryptography bases on the fact that there are two keys, a private one and a public one, where a public one can go freely all over the internet to end users, and the private one is kept safe. And those two keys can enable you to establish a secure communication between any two parties. And once we have the identity of your endpoint and you have the public key that belongs to them, that whole bundle needs to be verified. It needs to be authorized. Somebody needs to say, okay, this person or this website is who they say they are, and I attest to that. This is what certificate authorities do. So it's a mouthful, but basically that is the thing that is embedded in browsers or your Android OS or the Mac OS, whatever OS you're using. They already have certificate authorities based in them. So let me just go back one step and address those keys again. So in asymmetric cryptography, which basically symmetric cryptography says that use the same key for encryption and decryption, and asymmetric ones, they have different keys. So the one key is private, one key is public, and you can encrypt, decrypt with both of them inversely. So why it's so efficient is that calculation and determination of those keys is computationally, it must be efficient but to determine them. But in order to decrypt and encrypt, more specifically to find the original data that you're trying to send, it must be computationally infeasible to do without a private key. So the operation must be that extensive, that difficult. It must take that much computer resources and time that it's impossible to break unless you have the key. If you don't have the key or somebody else has it, then we're talking about a big, big problem, which we'll address later on. Okay, so the relationship with between those two keys is determined by the algorithm that's used to create them. We will not go into details there because it's a whole different ballgame and we don't have time for that. But to illustrate a bit more what's important here. So we said we have a private one that belongs to the owner and is kept safe with the owner. Safe is paramount here. The public key can go anywhere, so it doesn't matter where it ends up, it's meant to be used in such a manner. As for the encryption and decryption process, it is defined that the private key decrypts the message and the public key encrypts it, which means that when I'm trying to communicate with somebody, I send them my public key. The person I'm trying to communicate with will use some kind of message and encrypt it with the public key and send the message back. When I get the message, I must be able to decrypt it with my private key. And this kind of cryptography can be used without a secure channel, which means that you do not need, other layers of protection when you use this kind of encryption because it's impossible to break, let's say. Okay, and the third one is something that we will be discussing in more length later on, signatures. So as far as encryption and decryption goes, the algorithm is simple. Public key encrypts and the private one decrypts. As for signatures, the private key is used to calculate a signature. It's an extra layer of protection where you, as a person who wants to say this message is correct and this message is mine, you add some kind of signature to that message that can be, again, decrypted later on by a public key because they work in inverse. So digital signatures are something that is very important, and like I said, some countries use them as a legal means of, opening accounts, getting data from the government and stuff like that. So it's a binding legal document, basically. So how do you create a digital signature? Well, you use some kind of hash, a digest of the message that you're trying to send. And the question is, why not, use the whole message? Lengths of messages tend to vary, and calculating some kind of hash or digest basically determines that you have a fixed length of what you're trying to encrypt and send later on, and it's better done that way. It's more efficient, it requires less computer power, and so on. So a sender encrypts this hash or this digest with his or her private key, and when the recipient gets the message, they get to decrypt that hash and basically compare it with what was received in the message. And since the decryption and encryption go inversely, they are capable of checking whether something has happened with that message. For instance, if you change something in the message, the hash, the digest will change. And you will not be able to provide a different signature if you're tampering with it. Which means that when the message is received and it's been decrypted, its signature, the recipient will know, okay, the original hash that was signed, that was provided in the signature and the one from the message that I got do not match. And you can keep your users safe by reacting to that information. Okay, so basically you can state that this kind of communication, you have authentication because you know who the sender is. You also have something that's called non-repudiation, which basically means if I send some kind of message and I'm stating that my system is secure, I cannot later on say, okay, it wasn't me, somebody else sent it. If I say that, that means that my private key was compromised and somebody got it. So it's either or, basically. And the third one is the integrity of the message. You can verify that it was not tampered with in transit. So let's go back to our definition of a certificate. We have the identity of the owner, of the person who is saying, please trust me. We have the public key, which was defined and calculated by some kind of algorithm, and we have a certificate authority. Well, what is a certificate authority? Basically, it's a company or an entity that sole purpose is to say, okay, I issue digital certificates and you should trust me. It seems like a simple enough concept, and basically you're exposed to certificate authorities every day. So when you visit a website and you click on the bar, you can actually see who the certificate authority for that particular website is in the certificates. We'll get to that later. So certificate authority on its own issues certificates. And first certificate that they will issue is the one for themselves. So basically they are signing their own certificate stating, okay, we have a right to issue certificates, and by doing so, I'm issuing my own. A bit self-serving, but it works in the whole process. So the browsers, Android OS, Mac OS, everybody has predefined certificate authorities within the system. So when you get an update for your Firefox or Mozilla or any other browser, you should install the update because it probably has some modifications in the list of trusted authorities in it. If somebody was revoked, it will be removed. If somebody was added, it will be added. And basically that enables secure communication for yourself and the users on your computer. So what's stopping anybody from becoming a certificate authority? You can say, okay, I want to issue certificates and please trust me. So in order for your listing to get in all those browsers, you have to go through a rigorous membership program where you need to satisfy certain detailed criteria in order for you to create certificates and become an authority in it. So later on, when your certificate is added to a browser, it's basically transparent from that point on, and everybody trusts you. So how do you detect and how do you know that a website is secure? So there are two things you can check. Basically, you either have the name of the company in green at the address bar, or you have the secure with the little locket sign. The difference between those two is in the way how that particular domain was verified. There are two types of verification. One is domain-based and one is extended with additional checks. Domain verification is prone to attacks. How? Every now and then the certificate authority will probe you if you are an owner of a website, and they will try to figure out whether or not everything is still okay. They can typically do that by sending emails on predefined email addresses of your domain, like root or admin or something else. And it's been known to happen in past that some of the expected email addresses were up for grabs, which led to people basically opening accounts on Microsoft Live in Finland or something like that. The user obtained an address that later on led him to get a token or a key from a certificate authority. And by doing that, he could later on publish more certificates on his own. So basically, that's a huge breach. And the thing that's flawed here is the design. There is no extensive and final list of addresses that are expected to be, your point of contact. And the point is that only authorized personnel should have access to those email accounts. Extended validation, which is basically when you see the name of the company, is an added layer where they do not only say that you have the right to a domain, they also verify your identity. So you have to provide much more information. They call you, they tell you to submit some additional data, scan documents, etc. So it's basically an added layer of security. And the websites that do have extended validation are more safe than others. So let's take a look at Google. You probably won't be able to see the details here. So if you have your phones nearby or your laptops, you can just open google.com and take a look at for yourself. It's difficult to show here, but at the top you have like a small chained list of free things. At the bottom of the list, it's basically the Google's end certificate. By end certificate, it's basically the certificate that states that Google's identity is its own and it's trusted. I'm going to switch to the next slide. I'm just raising up through that chain a little bit. The middle one is, again, a certificate. And you might ask yourself, why do we need another one? Well, the middle one is actually what's called an intermediate certificate. It is used to verify the end one, to sign it with a signature, and to say, okay, the end certificate is valid, you're free to use it. And if we go one step further here, we will go to the root certificate, and this is basically what the VeriSign or GeoTrust or some other company is basically issuing to Google, saying, okay, I, as a certificate authority, claim that you are Google and you have a right to this domain, and people should trust you. Your browsers, seeing that they have GeoTrust in their trust stores, will say, okay, fine, we believe you, let's move on. You can take a look at any website and try to see what their certificates are. The novelty here is that Google is getting into the certificate authority business, and eventually they will be issuing their own, but it's not really ready yet. So if we take a look at the chain that we just observed, basically we have a root certificate, which is what the certificate authority signs. It's a self-signed certificate, and that one is used to verify the signature of the intermediate one. And then there's another hop that goes to the end certificate and says, okay, the end certificate is also valid, it will work fine. Now, Android needs a whole chain of certificates if you want it to trust communication with a server, let's say, that doesn't use a certificate authority that's trusted or new or something else. And when you, let's say, pin certificates, which is a security feature that you can use to state that the communication between your app and a particular server is trusted, then you need to add the whole chain. Now, what is the problem with this whole scheme? Basically, when one of the certificates becomes compromised, either somebody steals their private key or something else, the whole branch that is basically the roots that are rooted from it, the whole branch dies. So basically, you need to call all your clients and tell them, okay, this is not trusted anymore, let's reissue certificates and go from the beginning. So that's one answer to the question, why don't we just use the certificate authority root certificate to sign everything? If that one is compromised, then basically the whole part of the World Wide Web would be untrusted. So they're kind of distinguishing different companies and trying to delegate the authority to issue certificates onward. One example of that, I love to keep all my keys on one keychain. That goes to my apartment, my building, my family's building. I have my car keys on it, garage key, storage, everything. And I know by default that if I have my keys with me, I can open anything. But it also means that if I lose my keychain at any point in time, I'm going to have a huge, huge problem. A lot of people have to change their locks. I will be denied access to all the things that I'm used to. So basically, it's a compromise between practicality, what's easier for you and what's more convenient for you, and the fact that it poses a risk to us as users, your clients, basically anybody you can think of. So how do you prevent keys from being stolen? We're talking about private keys that will allow any kind of entity to continue issuing certificates. Well, their risk is theft. So anybody can try to get to them. It's not really that. It's not really easy to combat. The whole scheme is flawed because any kind of certificate authority decides on who they will issue a certificate to, which means that if they find some kind of shady company and they don't do the checks correctly and they issue a certificate, you're in big trouble because malicious intent is not something that's being checked. So we rely exclusively on certificate authorities to tell us what's safe and what's not, and that needs to be dispersed in a different way. What's typically done, the root certificates, their private keys are kept offline. So they're not accessible to anybody and they're not available online because obtaining such a key would be disastrous to the whole community and the World Wide Web. So typically what's used are hardware safe storage modules, and they are so safe. Basically those are little black boxes that require 5, 6, 10 physical keys to access and to unlock, that any kind of movement like earthquake, temperature shift, currency change, it will erase everything in the module. So it's very safe against tampering and stealing and any kind of manipulation, and that's typically where the keys are saved, and you don't have access to it. So it's in secure storage, they're offline, and they're only used when you need to temporarily sign some kind of intermediate certificate. So use it, remove it from the space. They need to be kept safe. So how does this actually apply to Android? So if you ever try to connect to a server that doesn't have a valid SSL through HTTPS and that is signed by a self-signed certificate, for instance, companies used to be kind of cheap and they wouldn't want to pay like a commercial solution to get a certificate, so they would make their own. They would say, okay, we are going to sign our own certificate, we're going to deploy it to our server, and we're going to connect our application. And there came Android and said, no, you won't do that. I will not allow you because I don't trust you. I don't know who you are. You're not the certificate authority that I trust. So what you would typically do before Android M, I think, or even before that, you would take that certificate and you would install it on the device. That would allow you to say, okay, my dear Android, you don't trust the server, but let me import that certificate on you, and now you're in the list and the communication will go on. And that is true. But with Android M, a lot of things have changed for the better. We got the security network config, where we can define what we trust, whether it's clear text or just HTTPS, whether we trust user certificates or just system certificates. Basically, it gives you a fine granulation of what your app will do and how it will do it. You can still get the same behavior where you can install the certificate, but you have to define it in your security config that you will be using your user certificates. So it is safe to assume that not anybody will get your device, unlock it, install random certificates, and then try to perform some kind of attack on you like a man in the middle. So we now know what certificate authorities are and why they are important. And now let's see what digital signatures are. So you have experience with building Android applications. You deploy builds probably daily, weekly, or whatever, and you certainly deploy a new build every day, at least when you're implementing something or creating some new features. Your APK is signed by default with the debug certificate. So you have a Keystore, which is a binary file that holds keys inside the SDK folder, and it's created when you start using it. And it's a debug Keystore, which means that it's not safe. And when you try to upload a debug build on Google Play, they will say nope again. The reason it's insecure because its password is Android. It's a well-known fact. It's a utility, it's a convenience for you as developers not to go through the signing process when you start developing. Now, since all APKs need to be digitally signed before they can be installed, you can basically create a key for your application and a Keystore to accompany it and to save it in, or you can use your debug Keystore. My personal suggestion here would be to create your own, because the debug, let's say you're working in a distributed team and there are, let's say, 5, 6, 7 developers, and your project manager wants to check on how you're going. And he's bugging you and he's bugging your colleague, and he says, okay, please deploy a build with what you've created now, and you just create an APK and send it to him or to her. They install it, check a few features, and your colleague says, hey, I've added something else, will you please check mine? If they try to deploy the same APK to that user, they will not be able to update the app, because the debug Keystore, the key, the certificate that's used, they differ between us. So each one of us has a different one. Its signature is different. And the application, if it's signed with a different signature, cannot be updated in any way. That's a huge implication, which will later be explained with what happens when you kind of make a mess with your actual release Keystore and the keys. So, in order to sign the application properly, let's say define a Keystore and a key for your application, and then say that all the members of the team are using it, because then the signature is the same and you can deploy the app regardless of who is making it. So basically, if you want to sign your application, and if you don't already have a Keystore, a custom Keystore for your build, the Android will greet you with this cute little dialog, which basically allows you to define the Keystore, where it is and where it will be used. You can define a specific key, a private key that will be used for your application, and you need to provide some certificate info. So identity needs to be known. You identify yourself or your company, so if you're the lead, then you might enter your data, or you have some predefined data that's used by all team members. So basically, you define all that is necessary here, and your Keystore at the end of this process will be created. When that is done, or if you had it before this whole process, then you're greeted with a simpler dialog, which basically just says, choose a Keystore, and within it, choose a key that's used to sign this application. Again, fairly simple. Now, what tends to happen at this point, when the whole process is done, you will end up finding your Keystore data somewhere in the build Gradle file. That means the password, the location, the file name, the alias, and the rest. And if you're working on an open source project or have a lot of collaborators, that's a very bad thing to have. We'll get to that later. We also have some experience with that and the problems that can happen from there. But what you typically want to do is remove that data from the build Gradle and access it from somewhere else. You might have a continuous integration tool that you're using, delayed and relayed the signing to that tool, or you might have the Keystore somewhere else and just access the data while you send the application. You should definitely keep it somewhere in a repository that's safe, but that repository should be different from the one you use for your code, just for an extra layer of protection. If you're old school and you don't like, using a user interface to do this, you can just use the command line tools that are accessible to you as developers. You use a key tool to define your key and a Keystore. You have the zipline tool that will align your APK. Basically, all the uncompressed data needs some kind of type byte alignment that will save some kind of memory, the amount of RAM that can be used later on for the application. So it's typically done at this step. And when you're done, you need to use the YAR signer tool to sign your application with the data you have. So the process is the same, one is more convenient, but you need not rely on Android Studio to complete the process. Now, we have some decisions to make. Who is responsible for the keys? Is it you? Is it your team members? Is it your team lead? Is it a chief technology or security officer in the company? What I've witnessed is that sometimes when you rely on life to go along happily ever after, you don't take much notice of this and you just leave your Keystore data in the build Gradle and everything goes on and the life is good. So we have this beautiful illustration by Google which says that what is typically done, the developer has their key, they sign the application, publish it, and the users get it. And there's nothing wrong with this process. It's been used since the beginning. Now, what we expect from this process is typically that your application can be updated. Now, we already said that debug Keystore has different signatures, places different signatures on your application, and you cannot update it between team members. So, obviously, if something happens to your keys, the release keys used for Google Play, you will have a problem with your app, which means that your users, so if it's a base of 10, 15, 20, 100, I'm sure there will be quite a lot of angry people regardless of the size of the base. But if your responsibility is like thousands or maybe hundreds of thousands users, that's a business problem that you don't want to have. Now, prerequisites for everything to work fine is that the signing key, again, is safe and that it's accessible. Those two are kind of working against each other because the more accessible a key is, it's probably less safe because people have access to it. And the reality is that basically people spill coffee. I love coffee and I'm sure a lot of you love coffee too. And people switch companies. And you might wonder what this has to do with the whole process. And I will share a story with you. So, a few years ago, there was this developer, John, who lived in a country far away, and he developed an application from start to end. He published an application on Google Play, everybody was happy, the customer was happy, the application was used, and later on, let's say half a year later or maybe a year later, John left the company and continued with his life. Maybe a few months after that, the client came again and said, okay, the app is well received, let's develop something else. And a new team member took over the app, started developing. They tested it, everything was fine. And the client said, please release it to Google Play. We want the update to go to our users. And at that moment, the team realized that they cannot do that. So they went to build Gradle, they see the data is there for the Keystore, but there is no Keystore. It's gone, missing. So they go to the GitHub repository, they go for the history, try to find when something was added or removed, and they see the exact time where reference and description in the comments was added, oh, new Keystore, release build, blah, 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 and still no Keystore. So after some kind of exploration, it turns out that the Keystore never ended up in the GitHub repository, which is great because I already said that it shouldn't be in the same repository, but the problem in this case, it wasn't in any repository actually. So how to fix this issue? You don't have the Keystore, you cannot sign the application, you need to convey that information to your client who will certainly be happy, not. And you take another look at the build Gradle file. And when you look at it, you kind of see that the path to the Keystore is something that's basically not supposed to be there. So it was, you know, the reference to the disk, the username, something, 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 not even remotely close to the path of the project and the workspace. So coffee is amazing, and I love coffee, and coffee saved us at this moment because it turns out that John spilled coffee on his Mac at some point in time. And that Mac was just, you know, okay, this is useless, we'll get him a new one. It was placed in storage and forgotten. So tragedy averted, password for Mac received, we managed to get the Keystore back. But people don't tend to be this lucky. And like I said, if you're an owner of the application that has thousands and millions of users, this is something you cannot let happen. It happens to everybody. So, you know, we tend to go through life thinking, oh, that's just silly. How could I misplace a Keystore? Nobody will take it. It might not be even malicious. You know, people have backup of their drive or something else. They could have the Keystore there. They can keep it somewhere on a public or accessible computer. You cannot influence people, and you cannot expect people to be rational. So it should be taken care of in a secure manner. Now, another beautiful illustration by Google. So they obviously see that there's a problem, and they are offering us a solution from last year. Basically, they are telling us, okay, so losing, you know, your keys is a big problem. It's happened to big companies, it's happened to known companies, and we're going to help you avert it. So they are letting you use your key and upload it to them and say, okay, Google, you keep my key and you release the app, and I will use a different key, an upload key, with which you can say, okay, you trust me, this is my application, and I can upload it. So you're basically deferring the drama of keeping your key safe to somebody who is more trustworthy, or at least you hope. One thing to know before you opt in for this program is that decision is final, which means you cannot say, okay, now Google, please don't do this anymore, I will just deploy it myself. You will need to create a new application with a new package name and do the whole procedure. So once you say, I want it, you're stuck with it forever. Now, you can choose between new apps and old apps depending on what your business need is. But if you have a new app, the procedure is fairly simple. You create some kind of key and sign your application. That will not be, you know, the end key. Google will create it for you. Google will tell you to accept their program, which you probably will. You can upload your APK to Google, and basically then they will create a signing key, strip the signature from your APK, and place the signing signature on that APK before it goes to the users. So you're signing with an upload key, and you need to keep that upload key safe. But if you kind of misplace it or it becomes compromised, you can contact Google through a secure form and tell them, okay, whoops, I messed up, I lost my key, John took it from me, we have a problem, and Google will reset or revoke that key and issue you a new one. So you have some kind of fallback if something bad happens. For the existing apps, you again need to opt into the whole procedure, and you need to submit your signing key to Google. So you already have it, you need to just kind of say, okay, we're surrendering it, keep it safe. You create the upload key, you update your key stores, because your key stores had the key that is used to sign the app, and it needs to have a reference to the upload key now, because that's what you'll be signing the application with. And again, the whole procedure continues. You upload the app, the Google strips the signature from the app and places the signing key on it. So, like I said, if the upload key is compromised in any way, you have Google to the rescue, which is much better than relying on a Mac somewhere in storage, still having a key store to somebody who forgot it. Now, we have we answered this question actually. We are either going to surrender it to Google, or we're going to keep on, you know, Russian roulette and depending on ourselves because we know best. And another decision to make, how will you sign all your modules and your application and your various builds? So I'm kind of partial to the approach where you sign everything with the same key store because it's convenient, and I'll tell you why. For instance, debug signing is something that I don't feel that it's particularly useful, because when working in distributed teams, it poses a problem. So you have your pros and cons, basically. Modularity, you can sign different modules of your application with the same one, and you can deploy them and update them, you know, separately. If you have some kind of permission-based sharing between the applications, you can only achieve it if the applications have the same signature, so that's a bonus. And your application can be updated from anyone and from anywhere who has your key. The cons is that you have a single point of failure. Again, this is more prominent if you're taking care of the keys yourself. If you're relying on Google, then it's not such a big problem. Now, just one quick illustration of the whole ecosystem. So basically, security on Android depends on how many layers of obstacles you add for any kind of attacker to get to your data and your information. And if there is any kind of access, there is a way to break something. So if we say that something is safe today, it may not be safe tomorrow. The security is basically based on the fact that you keep on pushing the limits with the tools that you have, and once they're broken, you go back to the drawing board and create something safer. And this is a normal process, and we cannot avoid it. It's what's pushing us forward. But the fact is that the more access you have to something, it's more open and it's prone to issues. Now, the Android Keystore system is something that's been present for some time now, and it's a great and convenient way to keep sensitive data in your application. It basically safeguards any kind of restrictive data that you don't want out in the open, and it doesn't allow extraction from the device. So it's a good thing. So if you have your keys at any key store and use it for any kind of cryptographic operations, so something top secret and secure, the key material that's linked to that key store cannot be extracted. It cannot be removed, transplanted somewhere else, and the other applications cannot get to it. It's physically impossible to get there. So restriction is good in this case because it can keep you safe. What's new is the Keychain API that was added in conjunction with the Android Keystore provider feature, but it was added in API 18, so Android 4.3. So basically any kind of security feature that you plan to use that depends on this, you know that you cannot apply it possibly to devices that don't support that SDK. And here is a short illustration of how important it is to not keep data in your application. Basically, if it's super secret and super important, if you can't do without it, don't put it in the app. So don't be lazy, don't be convenient, just remove it, keep it somewhere else. Deploy it on the server, communicate with it, but don't persist it anywhere in the app. You don't need it. And if the data isn't important, why are you adding it in the first place? So don't be lazy, just keep it clean, keep it simple, and keep your users safe because you never know who's going to go poking around your application. Now, one other problem that is that's huge. It's the extraction. So basically, you have the trusted execution environment on your Android devices, not all of them, those who support it, and basically the Android Keystore system will prevent any kind of extraction, which is good. Keys are bound to the TEE, which means there's a separate process and there cannot be accessed. Any kind of hardware backup is good because it's difficult to get to. So you can get to the data only under some specific, restrictions. When you define any kind of key, it's immutable. You cannot change it. You can issue a new one, you can revoke the old one, but you cannot change it. What's also important that there are 3 categories that fall into use of the Keystore system. Basically, cryptography, when you need to have some secret stuff that you're using for some kind of calculations or communication. You have temporal validity, which means that you can say that any kind of key is valid or accessible from the moment the user unlocks their device through a safe and secure manner, like the unlocking of the screen, and it will keep the keys accessible for, let's say, 5 minutes, 1 minute. You can define how long it is. And the user authentication, which basically allows you to say who it belongs to. So there are a few utility methods which are quite long and self-explanatory. It's easy to obtain any kind of information that you want. And one thing to decide is whether or not you will be using, let's say, a keychain for harvesting stuff and keeping stuff safe, or the Keystore provider. So the keychain is used to store some kind of system-wide credentials that are used all over the place. And it uses a system UI for you to access it and choose what you're using, and you need to provide a password actually. And with the Keystore provider, you can make app-specific credentials, which is a more clean way to do it, because then it's not, out there, it's bound to your application and it's not accessible. There's no interaction, you get to it in a different manner, but the downside is that it's available from Android API 18. So again, some limitations. So a quick overview how you can get to a Keypair entry and put it in the Keystore. You declare a Keypair generator, you initialize it with an alias and a purpose for which your key will be used. Now this is an added feature because you can say that your key can be used, let's say, for purpose of signing or verification or something else. Be specific. So don't be general if you don't need to be. You're making clean code, make clean security decisions, decide for what your key will be used. And then the system will enforce that use to be carried on. You can also say the algorithm in which the digest will be calculated. Some are safe, some aren't, some are accessible, some aren't, and that list will change with time because, like I said, security is ongoing and changing, and we make stuff better while we break it along the way. So to generate a pair, it's that simple. Now, if you want to list all the entries in a Keystore, again, it's simple. It could not be more simpler. You define a Keystore instance, you load everything that's inside, and then you just ask, okay, please list the aliases that you have inside. Simple. If you need to sign data, again, the process is fairly easy. You define a signature and say what kind of instance that needs to be used. You initiate the signing with the private key entry. You update the data that you want to sign, so it's basically whatever you're putting in the whole process, and you get the signature in a byte array. When you need to verify the signature, you just load the whole thing again. You initialize the verify procedure, and you just update the data and say, is it valid? Verify my signature. Now, another thing to keep in mind is the key attestation, which we have accessible. Basically, you can check whether or not any key is stored in a hardware-backed key store. First of all, you need to have a hardware-backed key store in order to use it. So you need to check for that. But this is a good information that will say, okay, the data is safe. We know that nobody can willy-nilly get to it, and it's a good added benefit. Again, the devices that will access it are 24+. So again, we have the ongoing issue with Android, which can be only described as fragmentation. So it's scattered. There are so many combinations. There are so many vendors. You have Samsung, which creates a new device every like 5 minutes, and they modify it and optimize it and improve it and add beautiful, applications in it, which you need to root the device to get rid of. So basically, it's chaos. We love the chaos, but it will render our progress, slow, and we need to be very diligent in deciding what features to use and for what. So you can have a handful of users that are super safe. You can target the whole, ecosystem, but then those features will not be available. So it's a business decision that you as developers need to inform your managers and the people up the stairs that implications exist and consequences can be devastating. Now, soon we will be getting a new version of the Android. My bet is that it's going to be Pancake. Nobody agrees with me, but hey, okay. Some new cool features are coming in. We obviously don't know the full details, but one thing is key rotation, which kind of the point is, let's say, missed now because we have the Google App signing process and we can defer the keys to Google Play. So we don't have to do it, but basically it allows a team of users to have different keys and just keep on signing them with one another. So you don't have to have one key for all team members, you can have several of them. And we have the Strongbox Keymaster, which is a Harvard Secure module. Basically, again, not all devices will have it. Some will be capable to have it, and then it will provide super secure storage on CPU, true random generator, because none of them are really true. To get the true random number, you really need to see what the alignment of stars is, if there's an earthquake in Peru, if there's some kind of cosmic, interference and stuff like that, because anything in a computer is not really, random. Two final thoughts. If you want to know more about the whole security aspect, something in the form of a report that's transparent and covers all the topics from SSL, secure communication, application signing certificates, there's a really great report from Google. It's accessible here, and you can just browse through the glossary and find out more information about the things there. And if you want to check whether or not your own domain and website are secure, I suggest you take a look at the Qualys website. The tests basically all the domains. You just place the domain inside and it will tell you what your grade is. Google is A, the best is A+, so they'll get there. But it can also give you a very long overview of all the security ciphers and else that are used for that particular site. And most importantly, whether or not a certain version of Android will be able to communicate with the server. So again, a business decision that might impact your users and your user base. And final thoughts for this, stay safe and make sure that all the best practices that you can employ in your company are employed. And thank you.
Awesome. Thank you so much, Anna. We are close to time, so I will open it up to 1 or 2 questions. Are there any immediate questions from Anna's presentation?
Thank you. That was a great talk.
Thank you.
I was wondering, particularly the part where we're talking about the distribution process, whether there's any tooling along the lines of what you can do with Fastlane for iOS to be able to automate more of that process that can still be done in a way that matches best practices.
So for iOS, I have actually no idea because I haven't been doing any Android iOS development ever, and I'm not sure what the team uses. There are some things that, so I cannot give you any kind of definitive answer, but as far as macOS and iOS users go, they have a secure way of doing more things than they do on Android, and I'm sure that they do have some kind of automated tool that can provide you with the same process. I'm just not sure what it is. So
I beg your pardon. What I meant was whether there's anything like that for Android, right? Something that would string together, zip-align, jar sign, all that kind of thing.
I'm not sure if there is a finished tool. So Fastlane is a great tool, and it allows you to deploy apps fast. Your company might have something custom in mind. I know that without going to much detail, companies tend to use different tools and scripts and other things that serves their purpose. So I guess the answer would be your business need probably tailors the tool that you want to use. If it's not accessible, you'll probably have to build it from scratch in some way.
Thank you so much.
You're welcome.
One more. Don't hold back now. All right, so lunch is being served. Thank you so much, Anna. Again, please, another round of applause.